Okay, so this is the problem that we started last time. We have this bar that's in torsion, and the internal torque is the same all the way along the bar. And so that t-value, that fancy t-value, never changes. And so any cross-section, we're going to get the same values, whether it's close to the wall or close to the left end, the values are going to be the same. But it's going to change as you go around the, as you go to different points in a cross-section. So first we did this point A. And remember that the way we do this, the formula says, this gives us the XY shear stress for a coordinate system where your capital, so we did this, so if we think about this point A, okay, we want this point here. And so we used a capital coordinate system where the z-axis goes out of the surface through that point, okay? And then the capital y-axis is like this, okay? And then once you're done with that, you do whatever rotation, but in this case, our x, y, z coordinate system is the same as our regular coordinate system, so we don't have to do any rotations. And so our shear stress, our total stress tensor for A is 0, negative 2.04. And that should have been negative, I think, Kale. Times 10 to the 7, 0, negative 2.04 times 10 to the 7, 0, 0. Okay? So now we're going to do the point B. And so this time, so here's our cross section. And we want to calculate the stress at that point B. So we need our temporary coordinate system, our capital coordinate system, to have the z-axis go from the center through the point. So this is going to be our capital Z coordinate system this time. And because of the right-hand rule, that means that our capital Y coordinate system is like this. Okay, so that looks a little crazy, but that's how we're going to think of it to start. Okay. But the formula says tau, capital X, capital Y is equal to negative torque times rho divided by I sub p. And so this is negative 4,000. The rho vector is from the centroid to the point that you care about. The total radius of this thing is 0.05. So the rho vector is 0.025. Are you with me on that? And then divide by the same. That polar moment of inertia doesn't change. That's just for the entire shape.
Quick question.
Yeah.
Can you demonstrate how to get your y from the z there?
Yeah. Well, you know that y cross z has to equal x. Or in other words, a rotation, use the right-hand rule, you rotate y to z, your thumb has to be pointing in the direction of positive x.
So when we take cross sections, x will be facing us.
Yeah, that's right. That's right.
Just generally.
Always. That's how I'm always going to do it. Yeah. I mean, you can also just think like this is a rotated version of the cross section you're used to, you know. So just turn the paper or turn your head. Okay. It's never going to be flipped. It's always just going to be rotated about X.
Yeah. Okay.
And well, since the only thing that changed here was the row vector, and the row vector is half what it was in the other case, I know that this value is going to be half of what it was, so this is going to give us negative 1.02 times 10 to the 7. Okay. So our stress tensor in this temporary coordinate system is 0, negative 1.02 times 10 to the 7, 0, negative 1.02 times 10 to the 7, 0, 0. Okay? Everybody with me on that? But this is not the coordinate system we want. Now we want to express this in the normal coordinate system. So we're going to go, we need to figure out the rotation matrix that goes from this to this. So what is that angle? Yeah. And it doesn't matter for 180 whether you go clockwise or counterclockwise. So our rotation matrix is cosine of 180, sine of 180, 0. Whoops. Be careful. Don't do what I did. This is a rotation about the x-axis. Okay, so this is going to be 1, 0, 0. 0 is down here. And then cosine of 180, sine of 180, negative sine of 180, cosine of 180. And so this is 1, 0, 0, 0, negative 1, 0, 0, 0, negative 1. Okay, and so now our stress tensor is Q times the stress tensor in the capital coordinate system times Q transpose. We're doing a rotation from a coordinate system like this to a coordinate system like this. You can do that as negative 90 or positive 270. About the x-axis. So that rotation matrix is 1, 0, 0, cosine of 270, sine of 270, negative sine, cosine. And the final answer for the stress tensor is Q times the capital stress tensor times Q transpose and this time you get a value of 0, 0, negative 2.04 times 10 to the 7, 0, 0, 0, negative 2.04 times 10 to the 7, 0, 0. Okay? And if you picture looking at this thing from the bottom with that same torque on it, what you would see is that on the positive x face, that stress element would be, it would be moving, like the right side of that stress element would be moving down in your view. And let me see if I can draw this. Okay, so here's the beam, and we know the torque is like this. Okay, and so now imagine that you're looking at this like this. There's your nose. Got your nose. There's your shoulders. Okay, are you with me on that? Okay, so what do you see? You see here's you thinking about it. An element that starts out like this and becomes deformed. I guess I always use red for this. I'm going to use red. Okay, so it starts out as a stress element like this. And it deforms into a stress element like this. Okay, so that means that your shear stress is going this direction. This is the x-axis. Okay, so that shear stress is on the x face. But what you see going up now is the z-axis. And so this is on the x face in the negative z direction. And so it makes sense that that shear stress would change to the xz element. Okay? It's really not that crucial that you do that, but it's always nice to be able to sort of sanity check your answers and make sure you're understanding this thing from different angles. All right. So now we're going to get into the second way that we can calculate stresses due to torque, and that is for closed thin-walled tubes. And so remember what this means is in cross-section we can do problems like this. We can do problems like this, where the thickness changes. We can do funky shapes. But what we can't do is shapes that don't connect. Okay, this is not closed. Yep.
You mentioned that the constraints might be on an electric switch or something. So for the closed thin wall tubes, are those the only two restraints, closed and thin walled? Or does it also have like a symmetrical or something?
No other restrictions. That's right. Okay, a wall thickness of less than or equal to about 10% of the total thickness is a good rule of thumb. Obviously, it's not a cutoff like 10 at 9.9%. It works perfectly, and 10.1% it fails completely. The thinner the walls are compared to the overall thickness, the better this is as an approximation. Okay. And you are going to, for these, choose a temporary capital X, Y, Z coordinate system with the Z axis, that capital Z axis, an outward facing normal to the desired wall. Okay, so for example, if your cross section looks like this, and you want to calculate the stress in this wall here, your temporary Z-axis would be this. That means your temporary Y-axis would be this. And that tells you what rotation you need to apply after you come up with your temporary values. Okay? Any questions about that? Oh, yeah.
That would be if we're trying to find the stress at that point.
Yeah, exactly. If you're trying to find the stress over here, then you're lucky because you just use the regular coordinate system and you don't have to do a rotation at all. You know what I mean? Because here an outward facing normal would be this.
Because it's thin, we don't choose a point on the thickness.
That is a really good point that I wasn't going to bring up yet, but yes, with this thin-walled tube approximation, we're assuming that there's no difference in shear force through the thickness of the wall. And obviously, if you look at just look at the formula for a solid tube, wherever that is, you have that that row value in the formula, which says, yeah, changes in distance from the center change the value of the shear stress. Okay. But as that thing gets thinner, those differences become smaller as you go through the thickness of the wall. What? Yes, exactly. Yep, exactly. Okay, and so now this is the hard part, the rotations, the visualizing and stuff. Applying the formula isn't too hard, but here's the formula. It's a new formula for thin-walled tubes. Tau, capital X, capital Y, is equal to negative internal torque divided by 2 times the thickness times the median area. So T is the thickness of the wall at the desired location. So remember that these thicknesses don't have to be the same on every wall, okay? So you'd use a different, like, look at this rectangular cross section I drew here with different thicknesses on all these walls. If you're trying to calculate the shear stress in this, point at the bottom, you use a different thickness than if you're trying to calculate the shear stress in this. Okay.
A quick question.
Yeah.
So for wall thickness, less than 10% of total thickness, would that be like the blank? Or what do you mean by total thickness? You mean like the depth?
I think it's more hand wavy than that. Call it the biggest length you can find.
Okay, so it could be like in the X direction or on the base of the cross section.
I got you. Not the length. Like the longest length dimension in the cross section.
Okay.
Yeah. So like 10% of this distance or something. Yeah, good question. So it's not that, it's the beam could be 1,000,000 miles long or whatever. It could be a foot long. That doesn't have anything to do with it. It's all cross section related. Okay, so T is the thickness of the wall at the desired location. What's this median area? I'm just going to draw a picture. Well, this is the area inside the median of the cross section. So let me give you an example of that. So for example, if your cross section is this, okay, then the median is just the center of the wall all the way around. And a median is the area inside that, including the empty space. Oh my God, I'm going to be drawing these crosshatches forever. Thanks. Oh man, I got distracted and messed up too. Okay, so that's what that means. One thing I want you to notice though, because there's some shapes where you know, say you have a triangular shape and like different thicknesses, and you're like, okay, where do these lines meet? And it starts to be, okay, so I want you to notice one thing. Don't kill yourself getting an exact measurement of that A median. These walls are thin. So thin walls means the area at the outer boundary is really not that different from the median area and is really not that different from the inner boundary area, you know. So don't stress out too much. You could calculate the area inside the inner boundary, the area inside the outer boundary, and just average them. That's not an exact value, but this is not going to change your answer very much. Where does that come from? That area median thing? Well, just like, remember when we did the shear stresses due to shear force, that Q thing comes up, right? That's like where you're measuring the distance to the centroid of this, blah, blah, blah. Okay, and it doesn't mean anything physically. It just popped out in the math. It's a way to organize the math. And the same thing is true here. There's no particular relevance to A median. It's just like in this long, painful derivation, at some point, they're like, hey, I can lump these terms together and it's exactly this median area. Okay, so don't try to understand why that is or anything. It comes from a long, tedious derivation. Okay, which I could not do off the top of my head. Any questions about that? Okay, well, given that, hey, I just thought of something. I actually thought of this like 14 years ago or something, but let's pretend I just thought of it now. There's one kind of cross section where we can calculate stresses in the wall in two different ways. So where we can calculate the stress due to torque two different ways and compare. And that is a thin-walled circular cross-section. Well, let's go through this in kind of like a general way. And so I'm going to use all general values for this stuff. And we'll just be able to see then in the formulas we get how these things are different and how they would deviate as the walls get thicker and stuff like that. Okay? So first, let's do it using, okay, well, let me first give you the problem. So let's say we have this beam and the length doesn't change anything. And we have this torque T applied. And looking at the cross section, this is our inner, and this is our outer. So let's first do it as a thin-walled tube. If you think of taking a cut, you have this torque T here. You have your internal torque, which is what we're looking for. And you can see that T internal is just equal to T. So that's the value we're going to use for these formulas. Okay. The median area is pi times the median radius squared. Okay, so that's going to be pi times our outer plus our inner over 2. You know, the average of those two squared. And so you get pi over 4 times the quantity r outer squared plus 2 r outer r inner plus r inner squared. And the thickness is r outer minus r inner. Okay, so this xy value is negative t over 2 times the thickness times the median area. So we get a 4 on top, and on the bottom we get a pi times r outer squared plus 2 r outer r inner. Okay, this becomes a 2 on top, and so we get, let's see if we can simplify this at all. So we have negative 2t over pi times what the, Boy, I don't know how I multiplied this out. I mean, I guess I got something so clean for it. Foiling it out, it seems like it should give you, so it would give you 6 terms. Some of them obviously cancel. Well, let's do it. How much time do we have? We'll do this and then we'll stop. So we got r outer cubed plus 2r outer squared r inner plus r outer r inner squared minus r outer squared r inner. So now I'm multiplying through the negative r inner minus 2 r outer r inner squared minus r inner cubed. And what can we group? So this groups with this, and this groups with this. And so we have negative 2t over pi times the quantity r outer cubed plus r outer squared r inner minus r outer r inner squared minus r inner cubed. Right?
Yes.
Okay. Well, so let's stop there. And next time we'll do this calculation, not assuming it's a thin-walled tube, just assuming it's circular with an inner and an outer radius. And we'll see how those limit to be each other as those two, our inner and our outer, become similar and stuff like that. All sorts of fun stuff. It'll be like Valley Fair, but with math. Okay.
And Valley doesn't include math.
Oh, hopefully they use some math. That's a really good point. I bet they did use some math at some point, but they try to keep it from the customers somewhat, yeah.